All right, so glad he came to fix the microphone. We missed the first a little bit, but it's okay. So will Zilla do something like this in the future? Who knows? But they're unlikely to try again and exact it the same way, right? Now, in order to understand one of the kind of models we're going to look at, we need to know what a Gini index is. Who has heard of it? Sometimes the Gini index describes the economy of a whole country. It might describe inequality, for instance. Inequality is how they usually describe it. So if we have like amount of total wealth, can you turn your volume down? Okay. Amount of total wealth. And then what percentage of the total wealth is held by a certain percentage of the people? You might say, okay, if 25% of the people have 25% of the wealth, that's a pretty nice thing. That doesn't usually happen though, does it? And then 50% of the people having 50% of the wealth, 75 having, 75% of the wealth. Does that ever happen in any country? No, typically what you hear about is like, the top 1% of people having, 50% of the wealth. And you might end up with some curve like this. Sometimes we draw the curve flips this way though. So perfect equality would be, that 45-degree line, this. But what usually happens is there's a small percentage that has more of the wealth, right? Well, this same mathematics is used to do tree models. Who here has heard of a tree model or a random forest, decision tree? So decision trees try to build a model based on some factor, some feature, one feature at a time. If you've got 10 features, maybe it chooses one of them and tries to divide up your data based on that. Like if we're going to try to, figure out which group of people are going to like a certain song or not, but we don't have features on which songs they like, we only know which movies they like. We'll choose a movie that tries to divide the group into the ones who do like the song and the ones who don't. Or maybe you know where they live, and maybe that correlates with which song they like. Now, this example from design books, you have, it's looking at the square foot of the lot, looking at the price. So right here, it's not just the price, it's the price is less than or equal to, I guess, 197,250. And if it is, you go this way down the tree. If it's not, you go this way down the tree. It would be like me going into this room and coming up with some feature about you guys. So how many of you are left-handed? Raise your hand. All right. That's not many. That's probably not a great feature to divide the group of, unless it's very predictive of something else. How many of you were born in the first 6 months of the year? All right, that's closer to half. That's going to divide the group into half and half. But what we don't know is what's the target variable we're trying to predict. So let's pretend maybe we're trying to predict if you're left-handed. So now we got two left-handers. Raise your hands again. Okay. Were you both born in the first half of the year or the second half? Second half. First. Okay. Then this is exactly the wrong feature to choose because it's split still. We want a feature that maybe puts all the left-handers in one group, or puts, has a group that has very few of both classes. We want less diversity in your outputs at the bottom. See, what you're hoping, let's say we're trying to predict that condition of the house, okay? That's the thing we're trying to predict. Have you ever played 20 questions? It's amazing that you really can get to anything in just 20 questions if you do it right, right? What you're doing is you're doing yes or no questions, just like this. This is a game of 20 questions. Is the house price above or below this? Is the square foot lot less than or equal to 70,000? If it's true, go here. If it's false, go here. If you go down this way, then you ask, is the square foot of the living space less than or equal to 605? It's just 20 questions. And at the end of the 20 questions, instead of saying, oh, it's, a bulldog, or it's a red Ferrari, instead of that, the answers to your 20 questions are these classes. Here, you're saying it's class 3 or above. Here, it's below 3. Here, it's 3 or above. Here, it's 3. Other decision trees give you something more specific, like it's definitely class 4. It's definitely class 5, or it's definitely class 4, or it's most. Some decision trees instead will give you a little regression equation to follow. Just like y equals mxb at the bottom. But that's all this is. It is a game of 20 questions, and the system learns it for you. How many of you have experimented with sklearn, scikit-learn? Scikit-learn has a decision tree in it already. And you can just follow the instructions and it will do this. And a random forest is just a bunch of trees. So it creates a random tree that does its best to classify your data. Then it creates another one. And sometimes they do 10,000 trees. And then it votes. All of them vote. And then you get a really good answer. These things do not take long to train, and they work really well. In a lot of situations, they work better than neural networks. This is a very powerful tool you should learn to use. Any questions? All right. Random forest, we just mentioned, is just a whole bunch of decision trees. Now we have this spectrum from more interpretable to less interpretable. What does interpretable mean?
If you look at it, you can see visually what's happening.
Yeah, understandable is another way to put it. Now, I think the least understandable are neural networks. They should be way over here. Neural networks are a bunch of matrices that apply things, and these nonlinear functions in between. What you end up with is this very powerful black box, and you're not really able to peer inside and understand. There's no intuitive way to understand, except with some exceptions like visual models. Visual models will have neurons that correspond or are activated by diagonal lines or horizontal lines or circles or squiggles or other patchworks. So those you can kind of understand what they're doing. They're building up from those basic patterns. But for linguistics, like GPT, there's so much unimaginable computations going on in there. It's beyond human comprehension to understand. And that's why they are not interpretable. I think k-nearest neighbors are pretty interpretable. We'll look at those. These, I think they're fairly interpretable. Decision trees, pretty interpretable. Logistic regression, we looked at that last week. That's one with the trues and falses. And you got this thing, remember that? That's logistic regression. Linear regression may be the most interpretable. That's just you got a bunch of dots and you put a line to it. And there's some other models up there. This is what support vector machines do. Now, I think we may have looked at this briefly. If we have a bunch of things in here, let's say we've taken pictures of cats and dogs and put them into a space. Maybe you got cats on the left and dogs on the right. The support vector machine will try to find this separation, a band in between the points. It's always linear. If it's not a line, it's a plane or a hyperplane, we call it. Now, sometimes it is impossible. Sometimes there will be, a blue dot, dark blue dot over here, or a light blue dot over here. And it's just impossible to find that perfect line that separates everything. So we'll have some outliers. And you can program in a way for it to accept a few outliers. In scikit-learn, it'll do this for you. And there's a parameter, which in scikit-learn they just refer to as C. This is one of the arguments of the function that will make it more or less accepting of these outliers. But I think this is an intuitively easy to understand one. Okay, supervised learning in general means you know the answer and you teach the computer to know the answer too. Why is chess always a supervised learning situation? You're teaching computer chess. So you always have an end goal. Yeah, and you know who wins. There's no ambiguity. I mean, there could be a draw, but typically it's not ambiguous. You're not trying to let it look at all chess possibilities and figure out, find some interesting clusters. It's more like you want to win. The goal is to win. And if there is a winner, it's not an opinion. It's a mathematical certainty. This is a supervised situation. Okay, what if you want to go from the East Coast to the West Coast and you're using Google Maps to get there? Is this supervised or not? Supervised, because you do either end up at the place you want to go or you don't, right? The path should be a path that gets you there without driving through a river or a lake or something in the woods. It should be just roads all the way. Now, the one part that you may not be able to do reasonably is it the shortest path? Have you found the absolute perfect shortest path? Why is that harder?
Well, there are different goals you can have, like what physically is the shortest path, what would use the least gas, what would be the quickest. So it's, even the question, like which is the best path, let's do another in the context of driving to the complex.
Yeah. Yeah, and it gets even more complex when you bring in traffic, right? Because there could be ways to go that are shortest or maybe use less gas, but there's a probability that a few hours from now there will be horrible traffic. So traffic variability be part of this. There's another mathematical reason why these are so hard, and it's called the traveling salesman problem. Anyone heard of that? So let's say you have two cities, you have to go to both of them. The shortest path is obvious. if you have 3 cities and you have to visit all of them, well, now we got a couple of choices. We can either go like this, or we can go like this, or like this, or like this. This, if you go here first, then there, that's definitely not the shortest path because you're doing the long thing twice. If you have 4 cities, you just multiply the number of possibilities. So before we had 1, 2, then 3, I guess 3 possibilities. Now multiplied by 4, but then you multiply by 5 and multiply by 6 and multiply by 7, multiply by 8. It goes up, the number of possibilities goes up so fast that eventually we don't have enough computing power in the world to compute them. It's amazing how fast factorials go up. Do any of you have Python in your computer right now? Start it up and import math. I think it's math factorial. And just tell me the factorial of, let's say, 5. Let's start it out. 120. 6. Keep going. 5,040. 8. 40,000 what? 9. Louder, sorry. 10. I forget the last 3. Okay, 11.
399168800.
Okay, just one of you. Louder.
399168800.
200.
Yeah.
All right. Then we are gonna in 12. Do 12.
47001 600.
No, I think I missed one. I mean, 12 times this one.
Oh, you added a 2 in the 11.
Oh,
Yeah.
all right. So as you can see, it'll be going up right here by a factor of 10, then a factor of 11, then a factor of 12, and just keeps going up faster and faster and faster. And very quickly, it gets to huge numbers. So we typically come up with a good enough answer. So when Google gets you across the country, it's not looking at every possibility. It's taking shortcuts to help it do it faster. But it is still supervised learning because you want to get to a specific place. Okay, now thermostat. Could this be considered supervised learning?
But just a side question, could our model be built off based on human error?
Yes, bad data is often where the human error comes in. Someone entered it wrong, or they recorded in meters instead of inches. What about a thermostat? Is this supervised learning. Supervised learning means you know the answer, you're trying to teach the answer. Think about this in terms of a learning system. You have some input coming from the thermometer. Thermometer tells you, oh, it's 60 degrees. And that's going to compare it to what? Where you set it at. Let's say you set it 65. And so it's going to say, you know what? We're a little too cold. And so the system tries to learn in the broadest sense, where the learning is just this one dimension, your temperature. And it optimizes the system, meaning turns on the heat for a little while. Then, if the room is hotter, this sensor is going to change, right? And then the input to the comparator now, it's going to say, you know what, hey, we're good. We're good. And then the loss will be 0, meaning the error is 0 now. And the optimizer won't have to do anything. And then it'll just keep doing this forever. This is what happens in a neural network. This right here is just a simplified version of a neural network that can recognize handwritten digits. For every one of these handwritten digits, we know the answer. Each one will be just, a small number of pixels, maybe, 100 by 100 pixels or even less. And someone will have written some number, and maybe it's not written perfectly, it's a little messy, but somewhere, someone will have tagged it and said, this is a 5, so that we know exactly the right answer. And maybe it's even super messy, but if we know the answer, we know the answer, and there's no ambiguity. That makes this supervised learning. So what happens is every pixel in the image, it's fed to its own neuron. Remember, every neuron is just a tiny little math problem. It's a tiny little part of the computer program. It takes in a number. And then it's gonna send it out to all the neurons in the next level. See that? Every neuron here is connected to all the neurons in the next level. So you have every pixel connected to its own neuron, and every neuron is passing on that information, but this time with different weights. Every one of these weights is its own little thermostat. Every neuron is its own thermostat. That's all they are. Thermostats with a little bit of math thrown in. So we can think about the whole system as a bunch of like a million thermostats. We can also think of the entire thing as its own thermostat. We got the same components. You've got some input coming in. The system does some math and churning, whatever, and it gives its output. Like the model, you can give it a handwritten 5, the model might say, hey, it's a 7. It's wrong. So what happens? You have some loss, some error. It's going to say, nope, you did it wrong. And if we go back to see what's underneath, you have the data coming in, there's some model, it gives an answer, and there's error. If there's error, then it adapts the weights. Adapting the weights is the same thing as turning on the heat or turning on the air conditioner. Every one of those little weights can be made higher or lower. So if you understand a thermostat, you can understand a neuron in a network. So it just cycles and cycles again and again through the data. just like your thermostat is always on, always sensing the environment and either heating or cooling. Until every one of these little settings are as good as they can be. Then when you show it, handwritten digit of a 5, it'll say 5. When you show it a 1, it'll say 1. When you show it a 7, it'll say 7. Image systems have gotten more and more complex over the years, but they still work the same way. Most of them, in the next chapter, we'll look at unsupervised, but most of these systems are supervised. Like the example you see right here is a visual network learning to recognize objects. And looking at a picture of a car, and it's going to say car. Now, the way it says car is there are alpha neurons at the end. And all of these numbers, the system will be forced to make those numbers add up to 1, like a probability. There's something called a softmax, which we use to do that. Softmax just takes, any set of numbers and makes sure they all add up to 1. So if we can interpret these last neurons as a probability, and we're looking at a picture of a car, we want one of those fields to be higher than all the others, right? We want the car field to be higher than all the others. And that's how the system says what it thinks. It says it through that vector. This is supervised learning. You know the answer. You've got images of cars and you know they're marked or tagged as cars. You get images of cats and dogs and vans and trucks and bicycles, people and whatever. And for every one of those images, we treat it the same way as we treated the others. Every pixel comes into a neuron and it goes through a whole lot of steps in the middle that you don't have to worry about. But then in the end, it gives you its answer. It's either going to have the highest number on the right answer, or it's not. When it doesn't, then there's loss, there's error, and then you adjust all the weights in between until it gives a better answer. You change the room, all the tiny little thermostats inside the system get tweaked little by little until the whole system works correctly. One fun thing about these systems is, see this little window right here? One of the things they learn to do is when they look at an image, look at it in small windows. First you look there, then you look there, then you look there, then you look there, and you do this all the way across the image. Then you come back, shift down a little bit, and you do it again. And they do this incredibly rapidly. And they actually even do it in parallel. So they're doing all those windows at the same time. Why would they do that? Why not just look at the whole image? Why do the little window thing? The sliding window.
It's nice to figure out what areas of the image are most useful for this.
Not quite, but you get in there. Area is important.
Finding edges and stuff.
Transformations is a good word. There's something called translations. In the image space, translation is when something is shifted left to right or up or down. If you do the little window thing, you don't have to have the model learn that placement doesn't matter. What you hope is that you can teach your model, maybe if you see something like this off in the distance in the sky, maybe it's a seagull, right? Now a seagull being here and a seagull being over here, it's really the same thing, right? But before they figured out this little window thing, these image recognizers, part of the image, they would learn to recognize the seagull here, but they would have to almost relearn from other data that a seagull can be here as well. So when you do the wood sliding window thing, the sliding window, it'll come upon here and it can learn what seagulls look like. And that same part of the model can eventually get over here and just confirm that it knows or learn better what seagulls are. Whereas before, if you had a part of the image that almost never had seagulls, and then you all of a sudden had a seagull there, it wouldn't be able to recognize it. Translational invariance. So whether it's left or right or up or down, it's invariant for that. Supervised learning. Okay. A language model is always trying to predict the next word. Is this supervised? Why not? Remember though, supervised means you have an answer and you're trying to get the computer to predict that answer. The way these are taught, they'll take a word that is there and they'll mask it out. And they'll tell the system that this is the right answer and you have to guess it. The system will try to guess it. So it is still supervised learning. Some people might call it self-supervised because you don't have a separate group of data that's considered the answers. You're looking in the text and you're saying, I'm just going to mask this word, randomly blot them out, then have the system try to predict what you blotted out. So since you are assuming there is a right answer, whether it's subjective or not, the system doesn't know that difference. You're just telling it, I know the answer, you try to guess it, and when you're wrong, it applies to loss, error. Are transformers taught with supervised learning? Transformers are like GPT and stable diffusion.
I'll say yes. Say humans look at their output and rate it.
There's that part too. That's the human reinforcement. That is after a lot of the training has happened. Like GPT stands for generative pre-trained transformers. And they're trained, the text ones are trained by masking words. They will block words out and have the system try to predict them. Or they will take two sentences and they will say, okay, sentence A and sentence B, they randomly pick two sentences that will one right after the other, and they will ask the network to predict whether or not they were one right after the other. Then they will take two random sentences in totally different places and ask the same question. And the network has to decide if these two sentences appear together or not. But it's a whole subgenre of what they call self-supervised. These markers do not last long. I've only used those like a couple times in this class. It's already dying. Now, self-supervised for text means you just take some book, you blot out a few words here and there, and you're going through it and having it predict what you blotted out. Does that work for images? Oh.
Well, I mean,
It does, you're right.
Yeah.
But how?
because you trained it with individual kind of blocks, it can kind of predict that it's most likely that even though a portion of it's covered up.
Right? Yeah, so you cover up part of the image, have the model try to predict the covered up portion, right? Try to fill it in. Have you heard the term in painting? You can do this on I guess Stable Diffusion and Midjourney, you can take an image. It could be an image that's real, like you take a picture with your friends, and then you can blot out one of your friends and ask it to do in painting. It might imagine for you some friend you don't have or something, or it might put a clown there, or who knows what. But it's always going to do something that looks reasonable given the set of all possible images. They train these things on, millions, hundreds of millions of images. But it does the same kind of thing. Now, diffusion models are really interesting. And the self-supervised idea, it does start to blur the line between, supervised and unsupervised, but it all comes from a need for data. There's a saying, there's no data like more data. That's the best kind of data, more data. So how do you get more data when you don't have enough? You take what you have and you do tricks with it. Now, one of the tricks they've done is you'll take some image and maybe it's a perfectly nice, crisp, clear image, okay? Nothing wrong with it at all. Then they add noise to it. And then they train a neural network to remove the noise. And it is still supervised because you already have the answer. The answer is the original image. And the input is the one with the random noise that you generated. And they got very good at this. Then they said, you know what? Let's make it even noisier. So they would take this one and add even more noise to it. And they found that they were pretty good at, turning this image back into this one. And that one, they can turn back into this. And they just kept going down the rabbit hole, making it noisier and noisier and noisier and noisier until it was totally unrecoverable. And then they just started playing. Like, what if we started out with something that truly was random noise? It's totally crazy. There's no signal. There's nothing in there at all. But they didn't tell them all. They said, hey, here's the image. Remove the noise. And these models, these diffusion models, started generating all kinds of beautiful things. And instead of, recovering some real image, it would, in a sense, imagine. And maybe it would make, a picture of a tree or something. It was always different. And it really looked like these algorithms were being created, truly created. Does anyone know how they got from that to what Stable Diffusion can do now, where you give it a prompt and tell it what you want? The model has some latent representation, something it's in its internal state. It's just a bunch of numbers, a bunch of matrices, and it's using that to generate this. What they decide to do is take the vectors they get from the transformers that are used, like GPT, for instance. GPT birds, a bunch of them, that instead of working on images, they work on text. And they'll say, let's just, we'll take some text, like apple tree, and they'll turn that into vectors. and they will incorporate those vectors in with the noise. It's just another one of the inputs into the model. And this model would generate something. And at first it was pretty random, but they were still getting images. Let's say they got a beautiful image of, something. Remember, it's coming from random to make a beautiful image, and it maybe just makes a mountain or something. And they do it twice. One with the vector for apple tree, and then with an empty one. So they do it twice, and you end up with maybe 2 images. And remember, at first, these things are kind of random and they're not very good. They get better with training. But what they saw is they could get the one with the tree information from the sentence. It would be different. However they were different. And then they tell the network to go in that direction. And they got it better and better until they could generate, from randomness, basically, a picture that really does look like an apple tree. Now, the other information that they're including in here is we have lots of captioned images on the internet, and there's huge data sets of them. So out there somewhere in the world, someone has a picture of a tree and it has a caption. So these models can also learn from this. In fact, neural networks became very important to all of our lives in 2012. The ImageNet moment, that's what we call it. When neural networks got better than all the other models, and then no one else could do that. And all they were doing was looking at images and trying to predict the caption. And they got less error than anyone else. All right, any questions? We're going to go to the next chapter. So we've looked at supervised learning. What the heck could unsupervised learning be? What does it mean?
No, like, goals.
There's no goal. Well, how's it going to learn anything if there's no goal?
You just kind of see what it makes, and then you either like, dislike.
Yeah. All right, let's look at some examples of unsupervised learning. One of the biggest areas is clustering. Clustering, there oftentimes is no knowledge ahead of time of how things are structured. You're trying to find out how things are structured. Unsupervised clustering is most of clustering. And remember, most of this is done in high dimensions. So you can't get an intuitive idea. It's just beyond your comprehension. You have to trust these coping mechanisms we have in software or in statistics. So you have a bunch of points. And you want to know something about how they relate to each other or how they're structured. These could be results from surveys. These could be results from blood tests. And you're trying to figure out how the population is grouped. If you have some new medication, and let's say you start to see some people respond really well to the medication, and other people don't respond at all. And then there's a few people that respond really badly and they get sick when they take your medication. It would have been nice to know ahead of time that someone is in this group versus this group versus this group. But maybe before you start, you don't even know those groups exist. You just assume this medication will help everybody. Unsupervised clustering can tell you things like this. Who here knows what a centroid is? Just raise your. The centroid is a center point in one of these clusters. And there's different ways to calculate that. We'll look at it. Density based is more like, okay, we're going to look for areas of high density. That's what I like better. We can also split clustering into flat and hierarchical. Flat clustering is we just do it once. Okay, here's a cluster, here's a cluster, here's a cluster. Hierarchical clustering says, you know what? Inside this cluster, here's a subcluster. And here's another subcluster. And here's a subcluster. And here's a subcluster. And within here, here's a subcluster. And a subcluster here and here. And keep going down. That's hierarchical. And my favorite kind of clustering is hierarchical, density-based clustering. And it's a very powerful tool for understanding things in higher dimensions. This is a Voronoi diagram. Every one of these points has a region around it that is defined by very simple mathematics. So simple. What do you think it is?
So you're coloring in the points where that like black dot is the closest to that.
Yes. Exactly. Very intuitive, right? This kind of thinking, you can look at it in a bunch of different ways. It's somewhat similar to, how bubbles form. Bubbles are minimizing the surface area of the sections that divide, or the lines that divide these sections. And it comes out to be similar in some ways to this math. And if you look at it in 3 dimensions, these things can get pretty complicated. But now, this is all based on centroids in a sense. These aren't exactly center points, but these are points where everything's closest to. And those points are what the system revolves around. But if you have a group of data instead of a region, and you want to figure out what's the centroid, well, there's more than one definition. Let's say that we have the light blue points, and the light blue points are our data. What is the center? The yellow or the blue? Which one is a better center? Raise your hand if you like the yellow better. Raise your hand if you like the blue better. All right. They're different. The blue is the center of mass, and the yellow is the geometric mean. So the geometric mean just means that this is the point that minimizes the sum of the distances. That equation up there. Arg minimum, the arguments that minimize the sum of the distances. The double lines 2 at the bottom just means the square root of the squares of the distances. That's just the distance, sum of the distances. The other one is the center of mass. You have an intuitive idea of what center of mass is. Like if I balance this pen, if I can get it balanced, it would be balanced on the center of mass, right? There, that's the center of mass. Now, if you have 2 dimensions, that'd be more like a flat object, right? If I were able to balance a flat object, it would be because I'm able to find the center of mass exactly. There. That is the center of mass of my phone. The center of mass of these points is the blue dot, and it's different. These are just two ways of thinking about it. And if we go back to that other thing, there's more than one way to think about this too. This is what we saw before. And every point in every region is colored by the black dot to which it is the closest with Euclidean distance. But that's not the only kind of distance. Who here has heard of Manhattan distance?
But just moving up further.
Yes, exactly. If you're in Manhattan and you want to go diagonally, you can't go in a straight line because all the streets are like this. If you're here, what's the distance to here? Well, I mean, Euclid would say this is the distance, but nobody in New York can travel that way unless you're on a helicopter. Everybody has to go here, 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 here. So if you have this distance metric, this is how that same thing appears. And there's other distance metrics you can use as well. K means is a certain kind of clustering. This is the math behind it. It looks harder than it is. And of course, when you do it for real, sklearn will just take care of that for you. Isn't that nice? You don't have to really understand. But it's good to understand it a little bit. What is the K for? K means, do you know? It's a number that you choose. You say, I'm going to say there's 12 clusters. You choose it ahead of time. In that way, it's kind of not unsupervised, right? You don't know where the clusters are, so it's a little bit unsupervised, but you're positing there's a certain number of clusters. So you choose a K, you choose it. Then you select random centroids. So it would be like, this kind of situation where you chose random dots. You chose how many? If I'm going to say 12, I just put 12 random dots. Then I figure out which data points map to each one using whatever distance I want. So you assign each point based on that distance. And here they are doing Euclidean distance. Then you recompute the centroids. That's what this is doing. This is really just averaging them. Now, look at that equation at the bottom. It's just summing up these things, dividing by the number of them. Is that more like the geometric mean or the center of mass? It's doing the center of mass. Center of mass is really just adding them all up and dividing. I mean, they actually don't show much dividing there, but the mass term is probably taking care of that. So what k-means is doing is you choose a number. Say, there's going to be this many clusters. You select random points. Then everything gets assigned to its nearest point. Now you have your clusters. Now, they may not be great, but this is only your first pass. Then you find the centroids. Then you go back to step 3. And you repeat 3 and 4 and 3 and 4 and 3 and 4 and keep repeating them. Let's say that the gray points is our data, okay? And we're just going to decompose our idea that there are 3 clusters. We choose 3. If you're right, we get it wrong. We're just going to choose 3. And the first thing we do is we put them in random places. We get 3 random dots. That's what the red, green, and blue are random dots. This is K means here. Then we figure out which points out of all our data are closest to each. And it's like that Voronoi diagram, right? We have 3 clusters. But step 4, remember, step 4 is recompute the centroids. So we do that. And when we recompute the centroid based on our data points, maybe we use center of mass, right? And that brings it here to here. And this one goes from here to here. And that one goes from there over to there. So we have 3 new centroids. Well, then we got to do that step again. And now we get different clusters. See that? These are in a different place than here. So we get new answers. And they look a little better, don't they? And you basically keep repeating that again and again and again until it stops changing. Stop changing. When it stops changing, then you just call it a day and say, hey, this is my answer. Maybe it's good, maybe it's bad. You have to use other measures to judge that. That's what k-means clustering does. Here's one I like better. It's called DB scan. First of all, we don't choose a number of clusters here. We don't know how many clusters. We want the system to tell us how many clusters there's. But we do have to tell it something. What we do, we tell it a certain radius to care about. And every point goes out in a circle or a sphere or a hypersphere around itself to see which other points are within that. And if they are within that, then if you have a bunch of points that are within each other's, then they form a core. And if they're on the edges, they're reachable, but they're not really part of the core. And if they're not reachable by anybody, they're outliers. It's a way to form an ad hoc kind of network of points, right? It's like a network. And you may have 1 core, you may have 100, and it's going to depend on how you set the radius, right? If you set the radius small enough, everything is an outlier, right? If you set the radius too big, what will happen? What happens if you set the radius really, really huge? What's the max? What would happen? No outliers. No outliers, and everything is in one cluster. And that's not really meaningful. You're trying to cluster and find, groups of people or groups of, data points. One cluster doesn't tell you much. So one thing that's nice about this is you can input any distance function. The normal one you put in, Manhattan, or cosine distance, there's all kinds of things you could do. And they're pretty robust to noise. Okay, this is just a bunch of data points. You as a human, instantly when you look at this, clusters jump out at you. It's instinctive. You don't have to think about it. Your eyes and your visual system are clustering this as we speak. Now, raise your hand if your instinctive clusters agreed with that. That's what most humans do when they see this. It was hard. It took a long time to get computers to be this good. A long time. There's noise in there. There's different densities. There's arbitrary shapes. Some of these clusters are weird shapes, and they're different sizes. K-means, the first thing we did, this is what it gives you. What's wrong with this? Where are the errors? Yeah, like this one, right? And this one. This should be one cluster. This should be one cluster, but it's not. Why is there a little bit of yellow in this cluster? It makes no sense. But this is what K means gives you. This is something we'll start with next time. Agglomerative cluster. Think about these being all your data points. Now it's representing them in one dimension, but you can easily imagine it in two or more. You start off by telling all the points, group up with your closest point. Maybe if I were telling all of you to group up in the clusters, you know, you can measure the distance to each other, and maybe the 2 or 3 of you that are the closest together in the class, you become a cluster. Then we increase our distance a little bit. Okay, the next closest ones, then they agglomerate. Then the next closest ones, they agglomerate. And then keep doing it. And of course, eventually, we're all one big cluster. And that's not very informative, right? So there's some right place to slice this. And say, let's stop here at 10 clusters or 20. This is getting closer to the kind of clustering I like. This is all unsupervised learning. All right, thank you guys. I will see you Tuesday.